Oh, for a muse of fire that would ascend the brightest heaven of invention. Should I go for it? Okay. Welcome everybody to the presentation of LCC Active. We are launching now a new surface technology that we have developed in cooperation with Technical University of Clausthal, TU Clausthal. And I'll be your host, Enis Aslanyuerek. I serve as research manager for LAUFEN Bathrooms. And that is a picture of mine a while ago, without a beard, longer hair, and so on. So, I'll try to use the pointer to point out. I don't know if it's very helpful. Yeah, okay. So, as I said, the new thing is called LAUFEN Clean Coat Active, so LCC Active. And I'll start by telling you what I will be talking about today. It will be, I don't like standing there. So what we have already had in the market for a while now called LCC, LAUFEN Clean Coat. And then I'll build my case to LAUFEN Clean Coat LCC Active by mentioning the market trend and the technologies, available technologies to achieve such surface. And the development phase kind of mention how it kind of worked out, and then the testing, and then I'm going to, summarize what I have talked about in the coming 15 minutes. So, what do we have? What did we have already is the LAUFEN Clean Coat, which gives us the smooth surface and hydrophilic property, which allows it to be cleaned easier, and it gets dirty. I mean, it is harder to get it dirty and easier to clean. That's the deal. Some microscope images for you to imagine how it could be functioning. Here you see microscope images of the standard glaze made in Gmunden. So, not the standard glaze made in Gmunden, but the images are made in Gmunden. So, the profile of the glaze, you see the main body, the ceramic body, and the glaze on top of it. And on the right-hand side, you see the surface of that glaze. You can see the surface defects through the shadows on it, right? So, and what LCC is pretty much better surface. As you can see, the excellent surface on the right-hand side, you see, it is a coat on the, it is another glaze layer on top of the glaze that we have already on the ceramic body. So, and here I have some more images, the 3D microscope, what we have in Gmunden again, to show you a 3D image. So the coloring is supposed to maybe give you a better sense of depth for that image. So what you have on the left-hand side is the standard glaze surface, and on the right-hand side is the LCC. But it is maybe harder to see here when one is looking at something from the top. It's harder to see the holes on it. So that program, the microscope, allows us to invert that image so you can see the surface defects just like the shadows that you have seen earlier on the surface image. Here you see the red peaks. It's just an inverted image of the surface. So instead of holes, you have peaks. And the red points, red peaks, are the holes on the standard glaze, which is normally is there, and LCC allows us to just cover that. How it has been marketed, so it is on the right hand side you see the image which we have on our website, so I kind of stole it from the website. You have the main ceramic body, it has the roughness that is given, yeah. The glaze which has much lower, much less of a roughness, and then the LCC, which is even better. So it is just giving you that hydrophilic, which you can see. What is hydrophilic anyway? It is just that droplet you see on the top of the surface, which is just flattened, so it's covering more. It allows the water, when it's flowing, just like in the vortex story, it just is supposed to take off whatever is on the surface, and that's what it does through that smooth and hydrophilic surface. So what is new about this LCC Active story? We have preserved our smooth and hydrophilic surface, but we have also now antimicrobial properties on that surface. What is the antimicrobial? It is a term that covers both antiviral and an antibacterial property. So they have both different testing methods, and our product now satisfies both these standards. Here you see an atomic force microscopy that has been, as I said, we have done that in cooperation with TU Clausthal. So the images of this atomic force microscopy images have been also made in TU Clausthal. You see that the standard glaze has higher surface roughness, and LCC Active has about the same roughness. What has been already, it has been already an interest of the sanitary industry, manufacturing, even before the corona crisis, the virus story, to have an antibacterial surfaces or something that cleans easily. And here you see some other, maybe some competitors, let's say, that are also advertising similar properties, but I have not run into any product on the market that has also claimed antiviral properties, which we have, as I said, through our tests and so on, we have seen that we do satisfy the ISO requirements. How do we even get such a surface? There are four ways I'll just mention now. There are stuff that are available on the market that could be applied, or applications available on the market that we thought that we could cooperate with these companies that provided for sanitary ware manufacturers. And for us, it didn't work out. I don't know whoever managed to get it through. And maybe you know the photocatalytic systems. Maybe you have heard it before, that you have some UV radiation in the toilet. You have this weird black light hitting on the surface, and they have titanium oxide. That is one way of doing it, anodized particles, that is integrated to the glaze. Once when the UV light hits on it, it just starts to catalyze, and that kills bacteria, or I don't know, whoever is there. So then on, there is also a way to manipulate, so improve the glaze itself to active, to participate in this catalytic thing on its own, so to say. But it is shot to almost 1300 degrees, 1300 degrees, and everything, almost everything reacts in that temperature. Think about your home oven, something, and if you heat it to 250, if you put something in there, it just reacts. And imagine that you are crossing now 1000 degrees, and in there everything glows and so on. Metal doesn't, but things start to react. So we stuck to another method, an antimicrobial coating. And how do we know how it works is the two standards, which involves you giving it you applying certain, let me switch to the other. Yeah, these are the ones. These two are the ISO standards that we say, okay, we satisfy the requirements to claim the antimicrobial function. So here we have two organizations we have cooperated with to make sure that they are independent organizations. We send our samples, actually TU Clausthal sent our samples, so we had nothing to do with the procedure, so they wouldn't be influenced by our interest or whatsoever. And so we have a piece, a sample of our product. On it, they just apply that virus or some strains that I'm going to later on mention, and after 24 hours, they see whether they are still there, or they have been mitigated or not. So how does a report of the sort look? And there, of course, there are more stuff that we'll look about, but here I will mention a couple. One is the roughness. It is rather, I have mentioned earlier, the contact angle of a, for example, water droplet on the surface. Here you see it on the third column. On the fourth, alkaline resistance. This is about what we use to clean our toilets, whether the surface is able to endure these chemicals or not. And antibacterial activity was checked. I mean, there is also antiviral, but as I said, I didn't add every column that we have checked for these analyses. And we have used the recipe that is now 5.2. It shouldn't delude you, it shouldn't mislead you to think that we had just 5 samples and just worked out. There is lots of research that went into that to end up with this. And we are always looking for better methods. Even now we have that product, we still look for other procedures, other applications, and so on to improve, to optimize our own procedure. So here you see some more of strains, not just E. coli. For the antibacterial activity, we have checked these 4 strains, not we, but the MTC lab in Germany. And for the influenza, it is like H1N1. Maybe you are acquainted with the grippe. I don't know if in English it is used, grippe. Anyway, so the flu, yes, the flu, kind of a flu. So, and we have all reports that it has functioned to meeting the ISO standards for all these strains, and so we can claim antimicrobial, which is covering, again, I want to emphasize, antiviral and antibacterial properties. Before I continue to my speculation, I would like to add now, if you think of an arms manufacturer that is just producing guns, they wouldn't be interested in telling you about how the bullet kills the person. So what I'm going to do now is to speculate about how this killing viruses and bacteria could be taking place. So we are using the active ingredient in our coating is copper. I'm allowed to say that because we actually have to say what we are using, because there are heavy regulations, European Union regulations on we have to declare what is in there because it's biocidal, so it's attacking something. But I can assure you there is no, so it is not toxic, it wouldn't poison the user, it's user-friendly and environmentally non-hazardous. So I will speculate about how it could be functioning, because even though we have also worked with the university, as I mentioned, nobody could just point out how exactly it works. But I will speculate, giving you 3 methods, that mechanisms that it could be functioning in. One is the so-called Fenton-like reactions. For the chemists might hide among you, I know that this procedure is a Fenton reaction, not a Fenton-like reaction. What you could see is the radicals on the right-hand side that form. It is pretty much the same once one uses copper, pretty much, but not the same, because it is heterogeneous, not homogeneous. So it is not in the medium, but it's on the surface. So it is the surface that is active, not something that dissolves into the system and then kills the bacteria or viruses. And as I said, it is the radical which is just reactive enough to attack whoever is around it. And once when that reaction takes place, it's just like corroding your hand with something hot or acidic or something. And then there is another mechanism, which I find also very entertaining. Here you see a molecule of hemoglobin, which allows your blood to suck through, diffusing oxygen in your lungs and deliver it to the cell that needs to breathe, to burn sugar and so on. What you might be not be able to see, this small stuff here has iron in it. So you have what gives its red color is the very iron in your cells, and that iron also allows it to fold in a certain way. And that very folding is the thing that makes it work the way it does. And proteins are having their own folding. Without that particular folding, they wouldn't function. That's why you die when your body temperature exceeds 43 degrees something. You denaturalize your body proteins. And copper could be also causing false binding and false folding of a protein, maybe on the surface of the cell, that could cause its death. And the last one, which I love the most, it is the destabilization of the cell membrane that could just open up a cell. On the right-hand side, you see an amazing video. I recommend to everybody to check this link out, to watch that video. It's just like 8 minutes. What you would see on the right-hand side again, okay? Here, a cell just loses a part of the integrity of part of the cell membrane, which then opens up and then spills all over, and that's how it dies. And that could be also a result, of course, all of these mechanisms could be playing a role, and none might be. It's just, as I said, it's a speculation to maybe give you a sense of scale of how it could be functioning. Now, to summarize what I have already talked about, without going into much detail, what we have is proven efficiency against bacteria and viruses, and it is not toxic, as I've said, so you don't have danger of if somebody's playing around, puts his tongue on it or whatever, they wouldn't be poisoned. It's environmentally safe. And we preserve the easy clean function, so it is as LCC, still easy to clean. And it's durable. It's another silicate layer on our glaze. That's how it is part of that. So that's how it functions, just doesn't wear off. So thank you very much for your attention. I hope I didn't take too much of your time for my details. Thank you.